Hello and welcome back. This video is to describe what happens to a air because it is overreacting and then compared to the figuring out figuring out what elevation condensation is and we begin again. Okay, so to start off with, we're down here. Sea level, where the temperature of the air is 94.5 degrees. We check the dew point temperature, that's the temperature at which condensation would occur. That's 50.5, which is significantly lower than 94.5. Because we are so much warmer than that dew point temperature, then a parcel of air is not sensitive. And so because of this, it's going to cool at the rise of adiabatic lapse. Now, obviously there is some moisture in this parcel of air, but until it's saturated, we're just going to use this. Okay. Before we really get going, one thing to just keep in mind, you don't have to worry about this in my assessment, but I'm missing a little. I'm just gonna... Now, the increment of elevation is matching. It looks like it's going up by 2,000 feet every time. And the dry adiabatic lapse rate is 5.5 degrees Fahrenheit or 1 feet. So if I go up 1,000 feet, it's like going up 1,000 feet twice. So 2 times 1.5 equals 11 degrees Fahrenheit. And we're going to be, what we're going to use 2,000 feet. So starting down here at the end, 94.5 minus 11, that's going to be 83.5. Now 83.5 minus 11 is 2.5. 72.5 minus 11 is 61.5. That minus 11 is 2.5. Okay. At this point, when our temperature of our atmosphere that we're thinking about is 50.5, that is the value of the dew point. Two things happen. One thing happens, saturation, right? At a temperature of 50.5 degrees, our atmosphere is saturated in condensation. That means physically that there was water vapor in this parcel of air and it condenses into a liquid. When you take a vapor and you condense it to a liquid, it releases latent heat, right? That's the heat involved in a phase change. So you have this phase change and you release heat into the parcel of air. That is going to enable it to keep rising. One of the things that lets it keep rising, however, it's going to rise at a slower rate now that it's saturated. So instead of using 11 degrees per 2,000 feet, we now need to switch to the saturated rate because our air parcel is indeed saturated with moisture. So the saturated rate is 3.3 degrees Fahrenheit per 1,000 feet, which is going to be 6.6 degrees per 2,000 feet. Okay, so now I'm going to let my air parcel continue to rise. I'm going to get 43.9. I highly recommend using a calculator here. And then I'm going to get 43.9 minus 6.6 is 37.3. And that's my temperature at the top of the mountain. From here, I need to go back down the other side, okay? Now, rising air expands and cools down, but falling air compresses and that causes it to heat. So we're going to be heating our atmosphere when it falls down the other side. Now, while it was saturated, it got rid of all the moisture it couldn't handle, right? So it stayed at saturation. It stayed at that level the whole time it was cooling. As soon as you heat it up at all, it's going to be capable of holding more moisture, okay? So as you fall back down the other side, then the parcel there is no longer saturated, okay? And you're going to be warming, you're going to be warming at the dry rate, okay? The dry rate, we remember, was this one, 11 degrees per 2,000 feet. Or you could use the original 5.5 degrees per 1,000 feet, which I think is what I'm going to do, because 5.5 for 1,000 feet times 12,000 feet equals 66 degrees. Okay, so we're going to have a temperature change of 66 degrees. We don't start at 0, right? We start with our temperature for the mountain, which was 37.3. We're going to increase the temperature 66 degrees, giving us the final temperature at the bottom 103. Okay, and at that point, we have this air rise up over the mountain. As it did, it cooled down until saturation was reached, until 100% relative humidity was reached. That's the same thing. At that point, condensation occurred, which added energy into the atmosphere, keeping it warm, changing the rate at which this thing cooled down. So it didn't cool quite as fast anymore because it was having all that heat dumped into it up until we get to the top of the mountain at that saturated rate. And then when we start compressing the air on its way down, it heats up, it's no longer saturated, and on its way down, we use that dried. Okay, so hopefully that helps, and you can all figure out exactly what happens to a parcel of air as it rises up and